I'd like to welcome everyone to the webinar series of the Cybersecurity and Information Systems Information Analysis Center, CSIAC. Today's presentation is entitled Rust Error Handling. My name is Steve Warzala, and I'm the CSIAC Outreach Manager. A few administrative notes before we begin. First, all phones have been muted except for the presenters. Questions may be asked at any time during the presentation by utilizing the chat function. And time permitting, your questions will be answered at the end of the session. Today's briefing slides and the webinar recording will be posted on our website within a day or two. And finally, I'd like to take a moment to acknowledge and thank our sponsor, the Defense Technical Information Center, DTIC. The funding that DTIC provides enables CSIAC to conduct these webinars. My pleasure to introduce our presenter for today's webinar, Dr. James Fawcett, a teaching professor emeritus of computer engineering at Syracuse University. Jim has 6 decades of experience in industry and academia. From 1991 to May of 2019, Dr. Fawcett taught graduate software courses focused on methods and strategies for the design, development, and management of large and complex distributed software systems. Prior to that, he worked in various roles for General Electric, including systems engineer at the Electronics Laboratory and developer and manager in the Radar Systems Department. Currently, Dr. Fawcett is developing a GitHub code repository, a collection of reusable software components with corresponding documentation and blogs. The site also serves as a platform for experimenting with methods for documenting and deploying code. I will now turn the presentation over to Dr. Fawcett. Good morning, Jim. The floor is now yours.
Good morning, Steve. Thank you. Good morning, everybody. I'm pleased to be here with you. I hope to share some of my enthusiasm for the Rust programming language with you. So with that, let's start. Before we dive into the material, I want to point out some links. Once the recording is posted, if you start it up and then pause it, you'll be able to access these links. This takes you to my main GitHub website, and there's the webinar slides that I'll be using today are posted here. All the code that we're going to get some quick views of the code. We won't spend a lot of time walking through it line by line or anything, but that's all available in this repository. And there's some other Rust-related materials there. So with that, let's start. So I want to take a couple of slides just to introduce Rust to you. I'm assuming that you had some interest stirred in Rust, but you're probably not a hardcore Rust developer yet. So let's go over some of the things that make Rust what it is. So Rust is a modern language, very much in the spirit of C++, that provides compiler-verified freedom from undefined behavior. I'm going to show you what that means in a couple of minutes. And it provides support for generating data race-free software. And both of these, the undefined behavior and freedom from data races, Rust provides the ability to do that in ways that are not available in other modern programming environments. So it's a big plus for Rust, and its performance is comparable to C and C++. Rust is a compiled language, doesn't use a garbage collection. In fact, it's based on its compiler is based on the LLVM backend, which is the same thing that G++ uses. And the intent of Rust is to take this experience that people have gained with C and C++ and develop the language that makes vulnerability, closes vulnerabilities by construction, and doesn't pay performance penalties for that additional safety, and at the same time enables you to develop abstractions that are necessary to build large code bases. And we'll see a little bit of that, but mostly we're going to focus on the error handling part. So Rust is quite clever. There are a lot of interesting ideas that Rust brings to the party. The Rust safety is based on a ownership policy. The idea is that there's only one owner of any piece of data. That ownership can be transferred or it can be borrowed, but there's only one. All heap storage is done through smart pointers. You can't get a raw pointer to heap memory as you can in C++. It's the only way to get it is using a box, which is really a smart pointer that when it goes out of scope releases the heap allocation, and consequently no memory leaks. Rust provides traits. I'm not going to talk a lot about traits, but I want you to know that traits are kind of like interfaces, and they're a little more than just interfaces, but you can use traits and the trait ideas to do polymorphic designs, to do dynamic dispatching, just like all the other modern languages. Rust doesn't focus on object-oriented design, but you can implement all of those ideas using the traits mechanism. So what we're going to focus on today is the error handling, and the next slide will turn to that. The Rust environment has a really nice tool called Cargo that supports dependency management. It does essentially transitive builds based on metadata that each Rust package provides. And the Cargo tool builds that metadata, and it provides ways for checking code quality, for formatting, doing documentation, and I don't think we'll have time to look at much of that, but this is a very effective tool chain. One of the things that people tend to like most about Rust, I think, is how effective its tool chain is. Okay, so let's turn to error handling. So the error handling comes at several levels. There's something called a panic, which is rather like a C++ exception. And it's the bottom level of the Rust error handling mechanics. Another part of that story is that any function that can fail returns a result that allows you to handle, if there's no error, the evaluated result of the function, or if there's an error, evaluate the, process the error. And we'll show you how all that happens in just a minute. We can, there's matching operations we can do that will illustrate, and event handling, we can bubble errors up the call chain, and this turns out to be a surprisingly useful mechanism. So we're going to talk about these four things. We're going to talk about panics, we're going to talk about returning results and matching, and finally bubbling errors up the chain. And here, if you follow this link, you can get to the code. It's the same code I showed you at the beginning. If you go to the home page of my website, link to the error handling code. And there's a series of podcasts that have been made available that are becoming available. I think there's 2 of them out now, 2 out of 5, on the Rust language. And so, if you follow along, you're interested in more of the details about the Rust language, you can follow up there. And you can follow up on my site. I have what I call a Rust story. Okay, so let's talk about error handling. So any function that can fail, Rust wants you to return a result. And I'll tell you in a slide or 2 exactly what this result is. But I want to point out here that Rust is it gets in your face. If you don't handle an error, here we're looking at a code screen, and this squiggly line is IntelliSense telling you, hey, you didn't handle the return that flush. There's a potential error in the flush argument that you didn't handle. And if you compile it, you'll get this warning. So again, it's getting in your face, hey, you didn't handle this error, which is a good thing. Okay. You can opt out of handling an error. In this case, the flush error handling is not particularly important, at least for the piece of code I was writing here. And if you name an identifier with an underscore or give it a name with the first character as an underscore, that's telling Rust, I don't intend to do anything with this identifier. So I'm opting out of handling that error. So Rust will let you do that, but its intent is that you handle all the errors that functions may return. Okay, so there's all kinds of errors, very low-level logical errors, indexing out of bounds, dividing by 0, integer overflow can be a pernicious error. Console and I/O failures are of course, common. Anytime we interact with a user, there's a potential for errors. System errors, anytime we interact with a platform, there's opportunities for errors. There's also, it turns out that Rust string handling is based on UTF-8 characters. These are characters that are multi-byte. A character may have a single byte, may have up to as many as 6 bytes. And the bad news is that makes it a little more awkward to handle. You can't index directly into a string. You have to enumerate them. But the good news is that you can represent all the international characters. You can represent Arabic script and Hindi Sanskrit God bless you math symbols and God bless you emojis or whatever you need to use. So all of these are sources for errors, and we're going to look at least a little bit at most of them. Let's start at the bottom. So panics are at the bottom of the Rust error handling chain. Panic is a program exit that unwinds the stack, attempts to unwind the stack, dropping each object that resides in the stack. That sounds an awful lot like an C++ exception in transit, and it's very like that. The developers of Rust came out of the C++ community, so it's not at all surprising that there's a family relationship here. If a second panic occurs while you're unwinding that stack, that causes an immediate program abort, just like a second exception. When there's an exception in flight, if you get a second exception, that will immediately abort a C++ program. The basic process is virtually the same, but panics are used in a different way, in a kind of an interesting way, as we'll point out in a minute. So these panics aren't accidental. They're intended program actions, And they're part of what prevent undefined behavior. We're going to show you that in just a minute. So panics are basically the lowest level of error handling mechanics. Here's a view of some C++ code and some Rust code that illustrates what we were just talking about. Here I have an array that I defined, and I am intentionally indexing it out of bounds. Let's see what happens. So here I am, 1, 2, 3, whoops. I was able to read this garbage memory location out of the bounds of my array. And not only was I able to read it, but my process terminated normally, gave me a normal termination. So that opens the possibility that I might walk away, my program might process this bogus data, and I wouldn't realize it. Let's see I'll come back to that point again in a minute. Let's see what the Rust code does. So I set up the same kind of example in Rust, and I indexed out of bounds 1, 2, 3. But here now, instead of allowing me to read memory that I don't own, it panicked. So this is the error, the lowest level of error mechanics in action. It's not allowing me access to that memory location. Now, in all fairness, C++ has lots of conventions that allow you to avoid this kind of undefined behavior. C++, for example, has range-based for loops in which you'll never index out of bounds. And we can get these same kind of errors by pointing with a reference internally to a vector or something like that. And if it reallocates, so you wind up with a dangling pointer, and you can do that in C++. You can't do that in Rust for reasons that basically the ownership policies prevent that from happening. But so essentially the model is this: C++ can be perfectly safe by convention. But Rust is safe by construction. So the real difference is, for writing small bits of code, relatively small projects, you can absolutely use C++ and write very safe code. But when you're writing several 100,000 lines of code, 1 million lines of code, it's very easy for code to sneak in that doesn't quite satisfy the standard C++ idioms, the conventions, okay? So C++ is safe as long as you follow all the conventions. Rust is safe because you don't have a choice, okay? They're compiler-enforced constructions that make memory safe. And data race safe too. We're not going to talk about data races today. We don't have time. But so, but in general, panics are the lowest level, and we really don't want to panic. If you're designing a flight navigation system for one of the big Boeing jets, you certainly don't want to have that code panic in mid-flight. Not a good idea. So, how do you avoid that? Well, basically, the answer is you handle all of the returns, these results, from any function that may encounter an error. And Rust does a really good job of vigorously reminding you about that. So here's the deal. Here's what a result is. A result is an enumeration that has 2 values. Now, in C++, we're used to an enumeration being a set of named constants, but in Rust, enumerations are more powerful. They don't just wrap. An enumeration isn't just a constant name for some integer value. An enumeration can wrap a type. So in this case, the result has 2 values. The enumeration has 2 values, OK and error. And OK wraps a t-type, which is whatever type the function is trying to evaluate. and it wraps an error type, which is whatever type the error mechanism returned to you if you encountered an error. Then Rust applies this attribute must use to this result. That's why you saw in the one of the opening slides warnings that you hadn't used that type. It's because we provided this attribute. The Rust provided that attribute for you. Now we can test these results. This enumeration has functions associated with it. There's an isOK function. So if my result is a T type, is okay, this returns true, and then I can handle this. And I handle this by unwrapping. What this unwrap does is it goes to this OK and pulls out the T type. And if my result is not okay, if is error, if that's true, then I can unwrap the error and do something with the error. Okay, really nice mechanism. So the standard IO crate, IO is a very common place for error results to happen. And all of the IO crate functions return a standard IO error. So Rust has defined in that IO crate a result of T, which is really just another name for this, just so we don't have to keep saying the same, typing out the same set of standard IO error. So in some of my code, you'll see what is really a result of T and E, but you'll see a result of T, and it's just because it's using this type definition. We can also create our own custom errors. So this use statement imports definitions from the IO crate. Think of the IO crate as a library. It's importing definitions of error and error kind from this IO library. And now I can build a custom error. I just say error new. It is creating an instance like a constructor. I'm creating an instance. I'm telling it that this isn't one of your standard kinds. This is another kind. And now I can give it some value. This could be an object. It could be a string, whatever my application needs it to be. So here's a little example of its use. So here I'm reading UTF bytes. So here I've got a vector of bytes, okay? I've got a valid vector of bytes. This is just the ASCII characters A, B, C. Here I've got a set of bytes that are not valid UTF-8. UTF-8 uses byte sequences to determine where the boundaries are between characters, and so you can give it an invalid set of bytes. And so when I'm converting into a string from that vector of bytes, I get a result. So this from function, from UTF-8 function returns a result. Here I am capturing that result. If it's okay, then I just process it as you normally would. But if there's an error, if I, for example, presented this invalid sequence of bytes, it would not be okay, and I could come down here and process the error. Really, really nice mechanics for handling. We can trap panics just like we trap exceptions in C++, not just like, but the same mental model as trapping exceptions. On the next slide, I'm going to show you a function. We're not going to walk through all the gory details, but we'll take a quick look at a trap function, a function that I wrote that will trap panics, just like a C++ exception handling does. Okay, so here, let me expand this. So here I've got a couple of functions that I wrote. Trap panic accepts a function. This particular version accepts a function that doesn't have a return type, okay? And so my result of running this trap panic, I want to, the trap panic is just a wrapper around this function. So I want this to behave like this function. And now this set of parentheses is called a unit. Rust calls this a unit, and it signifies that I don't really have anything to return. This is instead of using a null reference, it says this is a type that represents nothing, sort of like a nil. And now in here, notice that I have this panic catch unwind. So this is a function that the panic crate provides me, and I'm passing it a lambda. If you're not familiar with lambdas, this is just a very like a function. You'll find some discussion of lambdas in one of the podcasts if you're interested. Think of this as I'm just passing in a function. Could be a function that I passed it. And if it doesn't panic, then the result is okay, and I just return this, okay, I'm done. But if it does panic, then I can process that panic here. This function down here accepts a function that returns a result, and so here you see I'm returning the result from that function. And let's go over and look at the other side here. So this is my test for those panic functions, and you can see I'm supplying here all the things we talked about in one of those opening slides. Here's an out of bounds error, divide by zero error, an integer overflow error, initialize with non-UTF errors, and so on and on and on. And I'm just trapping them. These are like exceptions, and so you can think of this as just an exception handling mechanism that isn't the Rust idiom. The Rust idiom is that we'll handle this with results, but you can handle panics using this kind of trap functionality. Okay. So, but our main purpose is to avoid panics, not just trap them, but to avoid them. And so every function that can fail should return the standard result of T and E. And what that means is it's going to return one of two things, an OK that wraps the result value, or an error which wraps the error type. So here I have this function, and I'm decorating it with these generic parameters T and E, and I'm returning the result T and E. And so here, this is a function definition. So my function f, in this case, a little demo, I'm not taking any arguments, but I'm presenting results. So maybe I'm reading something from the environment or something, and I process code that can fail. And the result is an enumeration, again, that either returns OK or error. And then I can, as we mentioned before, I can test it. I can capture the result with F. I'm binding this result to F. And the type deduction that Rust provides makes this result have the correct type, this result type. And I can test it for OK. And then if it's OK, it's safe to unwrap. If I had an error and I just unwrapped it, this would panic. But if you test it, it's OK, then this unwrap will succeed and just return you this internal type, and then it just binds this internal type to T. And then I can do something with T. And the same way, if it's an error, I can unwrap the error and I bind it to this error instance, and I do something with the error. So that's the heart of Rust's error handling. There's more to the story, of course. There's a matching construct. So when I get a result, I can use this match result, and that sets up this OK. I can just say OK of T and just put my processing here in the air. I can put the processing here. So it's, it just helps me organize that a little bit. And match will require me to handle both of these. So Rust really would like you to use the match or something equivalent to it, because it's forcing you to handle both the OK result and the error result. And there's another little mechanism called if-let for the sake of the time available, let's skip over that, but same basic idea. And here's some code that, you know, does some error processing. Now, I created a function always fails, and I've got another function always succeeds, and I was using that to just as a demonstration for how this error processing works. So this function is always going to fail. It's always going to return an error. So this is really, you know, I'll never take this on because this function is always going to fail. And then I just demonstrate that I can print out this error message, and away we go. And here I'm using the matching construct. And in this part, if you're interested, you can come back and peek at it. I'm using this if-let construct. And this is not an assignment. This is a matching operator. What this equal sign here is saying is, does this result destructure into an OK? Does this result hold an OK? That's what that equal sign says. You know, it might have been nice if they'd made this an equal to make it a little clearer that it was a matching operation, but, you know, a tiny little quibble. Now, so you might be sitting back and saying to yourself, wow, okay, I got to handle all those errors. Now my code is going to get littered. Everywhere I have a function that can fail, I have to put this code that's going to handle the errors, and all of a sudden my nice, clean, understandable code gets littered with error handling, and the good stuff gets buried by all the error handling. Well, it doesn't have to be that way. There's a really nice construct called the try operator. This little equal sign is the try operator, and let me tell you what it does. So if G is a function that can return that returns a result, if the result is okay, it immediately binds it to this type, you know, and this has to match the right type or the compiler will complain. So this T has to be the same as the T returned by my result. But this try operator just binds the result. If it succeeds, it just binds the result to this value here. If it fails, it sends this back up to the result. It returns the error to this result for this function, okay? So here I have F calling G, and if G uses this try operator, it just bubbles the error. If there's an error, it just bubbles it up to the caller. And it's not at all uncommon to see a chain where a caller calls a function, and that function calls another function, and all the error processing bubbles up several levels. This in the model is very like exception handling. And in exception handling in C++, we may throw an exception, and it bubbles up until it finds an enclosing try block. Well, this is even a little nicer because here, you know, all we have is one little tiny character that will cause it to bubble up. So, you know, that works really, really effectively. I'm going to show you a little bit of code in a minute. Here's a little tiny bit of example code. Let me pull up, let's see if I can find another piece of code for you. Yeah, here. So here I have some error handling code I was demonstrating. And so here I have some file handling. And so here, I am using this bubbling phenomena here. So this create test file returns a result of a file, and I attempt to create the file, okay? And if there's an error, I'll bubble up that as an error. So this, remember that this result of file is really a result of file and standard IO error, so that'll bubble up that standard IO error. If that succeeds, now I want to write this content. So I'm supplying it a file name and I'm supplying it content. So I try to create that file. And if that's successful, then I attempt to write those bytes. But either of those could fail, and so they both have these try operators that bubble up. And so you don't see a whole bunch of error handling. I call the UABI, unwrap or bubble up error as UABI. So, and here's another function so here I created a test file, and now here I'm going to open the file and read it, and I do the same thing. I have this UABI. Here's this little try operator, and if my open fails, it'll bubble up the error, and then I read the string, and if that read fails, I'll bubble up the error. Really nice. I'm not littering this with a whole bunch of stuff. Now let's go down to where we're using it. So here I am not using those functions. I'm doing all of that without this try operator just to show you. And what you see is here I've got some error handling. And here I've got some error handling. And here is some error handling. You get the message. Here's error handling all over the place. But if I use those functions, I can use UABI here as well. Question mark, question mark. So here, no error handling at all. So what I'm trying to show you is that what may at first blush, handling all these errors, that may worry you that, oh my gosh, I'm going to litter my code with lots and lots of error handling stuff and make it hard to understand. That's not the case at all. This error bubbling is a very common, very common error handling mechanism in Rust. Now, let me warn you, Rust has a lot of really great documentation. In their documentation, they just unwrap stuff and they don't pay much attention. If it panics, there's a little demo if it panics, but it's giving you the wrong idea. You really, you want to use these error handling mechanisms this way. So let me put that back down, and now let's slide on. So very common error handling, console I/O, file I/O, socket. If I'm TCP processing with Rust has a very nice TCP layer, a thin layer over sockets, really quite nice. And, inter-process communication with pipes, and all of these, there's lots more, but all of these are good ways of generating errors. And I'm going to talk about these first two a little bit as long as there's time. So for console, the standard I/O crate has a function StandardIn that returns you a handle to StandardIn. And the intent is that you'll use that, you'll just use this, read line or read to string, and there's a ton more. There's, 20 functions maybe for StandardIn that allow you to do, reading kind of operations with your StandardIn. And notice that they're all returning errors. Now, what's happening here is this read line is returning a string as a side effect and returning the size of the number of bytes we read. That isn't because the Rust community has a strong affinity for side effects, is that the platform that we reside on has a side affinity for side effects. That's what the readers do in the C++ and that's what in the Windows platform and the Linux platforms, that's what they do, okay? Their functions, think of a socket function. You read, you're going to get the result as a side effect. And so this is just reflecting that, that kind of platform behavior. So, that's console I/O. And standard out has write all, flush, and tons more. These are really nice libraries, very, very nice, easy to use libraries. Same thing, we're supplying some material. You might ask, what's all this mute stuff? That's part of the ownership model. I'm not going to talk about that today. It takes a while to discuss that. there is a podcast available now on ownership. And if you're interested in that, you can take a look at that podcast. Okay, so here's an example. So I'm reading from StandardIn. So now this is a buffer that I'm going to read into, and this says import everything that make all the library artifacts available to me in this code. And now I print out, please enter some text, and I flush the stream just so I don't sit and wait in this read line, not having flushed it yet, not having passed this to the output. You have to do that with buffered output. And now, when I read the line, now I can match it, the result, okay, bytes, I strip off a new line and display the bytes, and otherwise I print out, it failed. And there's if you go to the code for this talk, you'll find this piece of code there, and you can pull it down and play with it. At the end, I'll show you where these are. And here is that I'm coming back to that string conversion, string from UTF-8. So here, if I provide a valid vector, then I get this writing. This is the output from the program, writing ABC. That's what happens here. And if I supply an invalid when this result is not okay, and then I'll come down and process this, and here's what you see. Invalid UTF sequence of 1 byte from index 0. It's telling you that I don't like this. This first byte doesn't match a UTF string. The UTF string can't start with that byte. Okay, I'm going to skip over this for the sake of time and talk a little bit about file I/O. So there's a very nice file system package, FS, in the Rust standard libraries. And it has an open that lets me open a file for read-only. It has a create that allows me to open for write-only. And I have options. I can truncate the file, or I can append to it, or whatever I want with this create function. And I can open it with options. I'm going to illustrate that just a little bit in the next slide. And there's a whole bunch more functions that you can use. But here's a file open that I wrote. Now, what I want to do is I want to do bit masking on a bunch of these attributes. I want to be able to say I want write and read. Maybe I want to both read and write to the same file. If I'm building a database record manager, for example, I need to read and write to the same file. I can by bit masking, I can pick any of these attributes I want with this one input here. So I am setting that up with a struct that has these constant attributes. Create is 1, append is 2. You can see I'm setting up bit masking with these. And then, I just do that. So here, now I'm supplying it. So here, for example, I'm testing these file operations. A result is open file for write, for create, and for append. Since I have create, it's almost certain to succeed. It would fail if I didn't have the create and the file didn't exist, for example. So now it's okay, and so, if it's okay, it's safe to unwrap, it won't panic, and I can just write out whatever, okay. Otherwise, I just display the fact that it failed. Now, here, the file does not exist. I picked this because, in my demo, I don't have a file with that name, and now I attempt to open it, and now I'm opening it for write and append, but I didn't include this create attribute, and so it'll fail. And that'll give me a chance to exercise that fail option. So really, really, really nice error handling. So Rust provides the very bottom level panics, and panics are partly responsible for safe memory safety in Rust. If I do something, you saw me at the beginning of this presentation index out of bounds of an array, and it panicked. And that panic prevented me from accessing that memory. Unlike C++, which allowed me just to go on and access that memory and, perchance to use it, panics prevent that from happening. So panics are an integral part of that memory safety. So what this says is, if you don't do, all your job with all this error handling stuff, we got your back anyway. What we'll do is, instead of continuing on and processing this, we're going to throw an exception. We're going to throw a panic, which is like an exception. So the standard result of T&E, the Rust tries to get you to handle both of these cases, the OK case and the error case, and it really gets in your face if you don't handle them all. And it'll let you opt out, but it wants you to handle both cases. And matching just as a slightly, sometimes a little less code rather than testing each of these options. And this called chain error event bubbling is a really, really, really nice scheme. It's this event bubbling that allows you to write code that isn't littered with error handling stuff. You just bubble it up to the site where, that one place in the code that is intended to handle that error. You don't have to handle it at all these lower levels. So Rust is doing its level best to prevent you from ignoring errors or forgetting to manage them. Okay, so and there's some references, Rust error handling. The Rust ecosystem has a whole bunch of really nice documentation. Rust tries to be very welcoming to beginners. It has great documentation, and there is a user forum called Discord, and they go way out of their way to be polite and gracious to beginners. Even you ask questions, they might groan inwardly, but they'll be polite and treat your request with respect. So it's really, really nice. It's a breath of fresh air. And this standard library takes you, there's a great documentation for the standard library. Here's all the pieces of the standard library, on and on and on and on. So it's easy to get to. Okay, and so that's it. I'm been pleased to talk with you about Rust. I think maybe you've sensed I have a lot of enthusiasm for Rust. I've developed a lot of C++ code, and I like C++ a lot. I started writing C++ code in 1988, and I've been writing Rust code now not quite a year, a little less than a year, and I'm really enthusiastic about it. I think they've done a lot of clever things in developing the Rust package, and I invite you to explore. I've tried to make it easy for you to explore. Let me go back and at the beginning, let me just cycle back to these slides for a minute, and then I'll handle questions if there are any. So let's get back to this very beginning. So here, okay, you can find, there's the slides if you go to this website. So it's, Jim Fawcett, one word, github.io. And all the code that we presented is in this error handling repository, okay? Rust panics, error handling, all the stuff that I showed you is here, so you can pull it down and play around with it. This is just my documentation page. If you click this link, this will take you to the real repository, and now you can clone it or download it or whatever you want to do. And I have a Rust byte by byte and a Rust story. The Rust story is kind of a narrative discussion, and it's essentially done. My narrative discussion of Rust This Rust byte by byte I am developing aimed at people who are just starting out with Rust. I remember the pain. There's some pain points getting going with Rust. I remember that. And so I put together, I'm putting together a sequence of, little factoids, introduction, data structures, life cycle. And you can see a lot of them aren't done yet. This is a work in progress, but I'm hoping by the end of the summer that'll be done. So there are places where you can go. And the Rust documentation itself, let's just pull up the Rust story for a minute. And now if I go back here, here's references, a ton of references. Getting started references, things you really want to look at right at the beginning, then getting started with references, intermediate references, some advanced references. These are references I put together as I was learning Rust, and they're one of the last things in my Rust story. So with that, let's stop, and I'll be happy to turn the floor over to any questions if there are any.
Okay, thank you, Jim. That was an excellent presentation. I guess one of the questions I have is, if somebody is a reasonably proficient coder, they've programmed in C before. So what kind of a learning curve do you think it is to pick up on Rust? And
that's a great question, Steve. Rust initially has a steep but short passage that gets you through the ownership policies. It takes a little while to get used to the ownership policies. Once you're used to it, it's a very fast learning experience. I find, for example, that when I write Rust code, I spend a lot less time debugging than I do when I write C++ code. And I'm really familiar with C++, okay? Because of all the mechanics that Rust provides me. There is definitely a pain point at the very beginning with the ownership policies. And so I put together a podcast on ownership, and there are ownership, for example, if you looked at the Rust bytes that I pointed out a couple of minutes ago, there's an ownership byte there. You're invited to look at that. But the Rust documentation is full of support and help for Rust ownership. So the best thing to do is just to write it. I think most people find that they're really quite perplexed for about a week, and then they start to catch on, and it takes them maybe a month to get really up to steam so that they're really entirely over that, mostly over the hurdle of the ownership policies. But the ownership policies are what make Rust what it is. Good question, Steve.
Okay, thanks, Jim. Yeah, that's so it doesn't seem like it's a if folks want to make the transition, that doesn't seem like it's a huge amount of time that they would like I said, for somebody that's knowledgeable in a other language to get up and running. So
I agree, Steve. Again, and there's lots and lots of help. So you have to write code. You can't learn something without writing code. But if you're from a C++ background, you'll find it really fairly quick. If you're from C or Java or C#, maybe a little longer, but it's absolutely doable. I promise you it's doable. I'm an old guy. I can do it. You can do it too.
Okay, great. So I guess, another thing, that I'd like to, ask is, so you've talked about, given the nature of the Rust programming language, it's it's helpful in creating assured software. And you've noted that there's not really a performance penalty, and there's not degradation where you're it's taking longer to run or things of that nature. So I'm just curious, do you see any other downsides with it? Are there any shortfalls or shortcomings with it, in your opinion?
So let's go back to the beginning. So you say, is that possible? You get, all this safety without a performance penalty? You got to be kidding me. Well, what happens is that compiles are slower because there's something called a borrow checker that's doing all that checking. I've built some fairly big stuff, and the tool chain is really excellent. Once something is compiled once, it does really good caching, So builds aren't a problem, but the first build may take longer than you might expect, longer than a C++ build would take, because the borrow checker has to do his job. After that, there's several models that are unique to Rust, but I think once you're over the ownership model, most of the rest of them just make a lot of sense. So, let your common sense and, eyes open and a cup of coffee in your hand. And I don't think people have a whole lot of trouble writing really good code. The tool chain gives you a lot of help with that, Steve. For example, the primary interface to the tool chain is a nice package called Cargo. And Cargo does the builds, it does the execution, but it also, you can run, if you say Cargo Clippy, it runs this lint checker through your code to see if you're writing Rust idiomatic code, like the way the Rust community thinks it ought to be written. And it's really good. I run Clippy on my code. Occasionally, I would say, nah, Clippy, I disagree with you. I'm going to leave it the way it is, mostly because, I ran Clippy on one of the examples I showed you, and it complained about a couple of things. And it was because I had stuff that I was trying to show you this option versus that option, So between Clippy and the documentation is great. If I use, for example, when I'm building a big project, if I'm using the source code, I can look directly at the source code. If I don't understand how something works, I can go look at the source code, and the source code is really well documented. I don't think we have time to look at it today, but really easy to get to. Rust also has there's a facility called crates.io, a website called crates.io, where Rust developers post things that are not part of standard Rust. Maybe they aren't part yet, or maybe they never will be, but they're available for anybody that wants to use them. And the Cargo tool, if you cite one of those on a dependency, it'll just go pull it down and build it. So makes it really easy.
Okay, so it sounds like there might be some additional time up front in getting the code ready to run, but the once you get to the runtime execution, it's pretty similar. Then it sounds like.
Yep. Well, the execution is every bit as fast as C++, and as well, the code development gets, in my mind, my impression, my reaction is that I develop code faster in Rust than I do in C++ because of the tools and the really nice tool chain that are available to me.
Oh, interesting. Very nice.
One thing there is one issue that I ought to point out, and that is there is no debugger as part of the Rust tool chain. And you can say, oh my gosh, that's a real showstopper. Well, it turns out it isn't, because when the compiler is done checking stuff, almost all the errors that you would normally chase down with a debugger just aren't there anymore. I don't miss it. So, and you can use, there's a GDB debugger, and you can use that. I'm not a big fan of GDB debugger, but you can use it, attach it to your code. I told you that Rust, the back end is LLVM, and GDB knows how to hook into LLVM. So you absolutely can use the GNU debugger for your code if you want to, but I think you'll find that you really don't need it, which is amazing. I wouldn't have believed that. If I was out there in the audience, I wouldn't believe it. Okay, that's what this guy talking about. But I think if you decide that you're going to give it a try, you come in and start writing some code. After you get over the ownership hurdle, you're going to come to the same conclusion.
Okay, great, thanks. So one of the attendees notes that they're interested in trying to learn more about the error handling. Try to use the traits focused on error handling. Is there a place where they can learn more about it? Do you have stuff on your site?
Yeah.
Or
So there is. So let me come over here and point that out. There's a bunch of places, but if we go here, in this Rust byte by byte, no, I have not. So in the Rust story, in the operations, I think, function error handling. So I have, some more discussion, some more examples in this Rust story. So for the viewers, this on my website, I have several stories, and the story is just a collection of a sequence of pages that are focused on a particular topic. And this Rust story is just a narrative discussion of the Rust language. And so there's some material here, and they have examples. You can pull it up and look at a little demo code. You can pull up and look at some more application specific. But a great thing to do is to look at pull down one of the crates or look at some of the error handling in the Rust source code. Let me show you how easy it is to get to that Rust code. So now, let's see. I got to let's go home and go to. Let's just do this. So let me say here, Rust standard lib. And here, standard library. So now I quickly repeated this. So you can go and pull down, I can go to collections, look at, if I want to look at the source code, so let's go to VEC. Here's VEC. And, I can pull up the source code, I can look at the source code, and I can see it here, okay? And so you can see the error handling that these guys are using as they're building the parts that make up Rust. But, I've got lots of examples, lots of example code on the website. Let me go back to that again for a minute. So if we go back home, there's these repositories. Here's the Rust repositories. And so here's some tools: Rust Logger, Rust Text Finder, components, libraries, command line display lib, demonstrations. Here's the Rust error handling that we talked about. So if you want to go back and look at that code, right here, it'll take you to this thing we looked at, and here's this handling code. You can just, and you can go to the repository and you can download it. Now, it's easy to get started with Rust. All you got to do is go to the Rust site, rust.org, and follow the download. You download it in 5 or 6 minutes. You'll have Rust up and running, and you'll have the cargo on your command line. You can open up a command prompt, run cargo. It's easy to get going, really, really easy. And in my beginning of my Rust story, I have in the beginning of this Rust story, I tell you a little bit about how to get going. You go to the Rust tool chain, pull it down, Visual Studio Code. Now you start, and on the next page, I did exactly, here's a hello world in Rust, and I'm telling you exactly how I built it and so on. So, all of that is here. If you read through a little bit, so let me get that. Here, I'm really walking you through. Here you are getting going, you're pulling up cargo, you're running it, so. Okay, I hope that answered the question. Maybe the answer was too long.
No, the individual found it to be very useful, and thank you for that. So,
okay.
So yeah, that's great, Jim. I mean, I thank you for taking the time to share the info with us on Rust, and I'll mention, we've released 2 of your podcasts. And we'll send out issue the 3rd one next week on the object model, and we'll finish up with a couple more in the July timeframe. So really, really appreciate you taking the time to enlighten the community on this new programming language. I think it's I think it has some potential great benefits for the development community. And, thank you for sharing your information and expertise with us. We appreciate it.
It was my pleasure. I've gotten messages from a couple of my former students. I see them here in the attendee list, and I was delighted to have this chance. I'm really enthusiastic about Rust, and I hope I can convey some of that enthusiasm to everybody. So thanks for the opportunity.
Okay. Thanks, Jim. Thanks for the audience for attending, and we look forward to seeing you next month. I think we're going to be talking about cyber physical infrastructure test beds. The date time TBD. It could be the 15th at noon, but we will send out an announcement with the firm information on that. So until that time, take care, everybody, and we'll see you in the future. Thanks.
Thank you all, and goodbye.
Bye-bye.